For weeks, the world's largest telescopes, Hubble, JWST, and Gemini South, tracked the enigmatic interstellar comet 3I/Atlas as it sliced through the inner solar system. Then abruptly the observation stopped. NASA went silent. Data streams froze. Into that void, China emerged. From observatories in Yunnan, Tibet, and Xinjiang, new high-resolution images began to appear. Frames captured the green, glowing comet invisible to other eyes. Western scientists called it coincidence. Whispers of censorship spread elsewhere. But the revelations from these telescopes were never just about a comet. They exposed who sets the narrative of discovery when the universe opens its door. When the faint object, labeled 3I divided by C divided by 2025 N1 was first spotted on July 1st, 2025, astronomers immediately grasped its significance. Its hyperbolic orbit, with an eccentricity exceeding 1, marked it as only the third confirmed interstellar visitor after Oumuamua in 2017 and 2I/Borisov in 2019. For weeks, observation data flowed from NASA, ESA, and premier facilities like Hubble, JWST, and Gemini South, sketching the outline of an alien comet hurtling through the solar system at nearly 60 kilometers per second, faster than any planet. Initially, the global astronomy community worked in concert. Chile's 8.2-meter Very Large Telescope recorded the comet's magnitude around 14.5, while JASITS captured infrared spectra showing unusual gas signatures. Then a gap emerged. As solar elongation dropped below 30 degrees, the comet sank into sunlight, making it nearly impossible for Earth-based observatories to track. Hubble's imaging schedule was fully booked. JWST entered thermal protection mode. Even Gemini, with its twin 8-meter mirrors, faced downtime. For 10 days, Western observatories went dark. Into that vacuum, Chinese facilities in Yunnan, Xinjiang, and Purple Mountain released high-resolution wide-field imagery of 3I/Atlas. Equipped with newly upgraded 4K CCD arrays and automated tracking, they captured the comet precisely when Western systems were blind. Images appeared online within hours, often with brightness estimates and trajectory overlays. Suddenly, the narrative shifted. Where NASA once dominated the visual record, Chinese images filled the silence, clear, timely, unfiltered. In those frames, the comet's green coma shimmered under sunlight. For many, the symbolism was unmistakable. A new contender had entered the race to decode rare cosmic visitors. These images didn't just cover gaps, they extended the timeline. Lijiang Observatory in southwestern China released a sequence of 12 180-second exposures stacked into a crisp time-lapse, showing the coma expanding to nearly 600,000 kilometers, its tail stretching across a star-studded background. Shingon Station near Beijing and Ali Observatory in Tibet followed, producing wide-field mosaics spanning 3 degrees of sky, tracking subtle brightness shifts as 3I/Atlas sped toward perihelion. Between late August and early September, when Hubble and JWST were offline, the Chinese observatories continued monitoring. Their data revealed fluctuating coma density and faint jets unseen before. The National Astronomical Observatories of China reported a 0.8 magnitude increase in just 3 nights, evidence of renewed outgassing or internal heating. High-resolution wide-field CCDs, automated scheduling, and flexible operations gave Chinese teams an edge. Each frame, time-stamped to 0.01 seconds UTC and cross-calibrated against reference stars, became a continuous record during a critical blackout. For researchers, this meant uninterrupted light curves and tail morphology, allowing precise modeling of outgassing and solar wind interactions. Symbolically, it rebalanced global astronomy. As Chinese telescopes illuminated the sky, Western observatories remained silent. Questions arose. Why was NASA seemingly withholding data? The last public Hubble UV images from July 21, 2025 showed a faint dual tail and expanding dust coma. After that, data releases slowed and raw FITS files took weeks, sometimes lacking calibration. Online forums and independent astronomers speculated, some accusing NASA of suppression. Official statements cited protocols, quality control, and instrument safety, but the optics were poor. The timing coincided with China's surge in output. NAOC hosted images within hours. NASA's database lagged. To the public, it looked like censorship. To professionals, bureaucracy. Either way, perception hardened into narrative. The issue was timing. Western observatories faced glare, fixed schedules, and expensive optics. China's agile networks contrasted sharply. Headlines across blogs and think tanks accused NASA of suppressing unusual images. In truth, Western facilities were simply offline. Chinese ones were not. Once that perception spread, it traveled faster than the comet itself. The debate over control of 3I/Atlas became as charged as the science itself. An argument over ownership, transparency, and the politics of seeing. Beneath that tension lay a deeper truth. Whoever controls telescope time can shape understanding of an interstellar world. 3I/Atlas is no ordinary visitor. Traveling on a hyperbolic orbit with eccentricity around 1.036, it is unbound to the sun. It came from the stars and will return there. Every second of observation is precious. Its inbound velocity exceeded 58 kilometers per second, enough to cross the Earth-Moon distance in under 2 hours, nearly triple the speed of typical comets inside Jupiter's orbit. Its composition, dust, and radiation response could illuminate how star systems exchange material across interstellar space. When astronomers study 3I/Atlas, they aren't observing a random rock. They're probing another solar system's chemistry. Its coma exhibited a CO2 to H2O ratio of 7.6 to 1, far from the 1 to 2 typical in local comets, implying formation in an extremely cold, distant environment. Missing observations would not only lose data, it would forfeit a piece of galactic history. Interstellar visitors like Oumuamua and Borisov were visible only briefly. 3I/Atlas offered roughly 90 days of Earth-based visibility. When NASA's major telescopes went offline due to solar elongation and thermal limits, crucial observational windows risked vanishing. Every missing night meant lost insight into jet shifts, tail formation, and chemical evolution. Control over telescope time is not prestige, it's authorship. The first to publish images, spectra, and models sets the baseline. With Chinese data covering the blackout, their teams now hold unique snapshots of an interstellar comet evolving in real time, unseen elsewhere. As 3I/Atlas brightened toward the sun, the question shifted, not just what could be seen, but who could still see it. It became a contest of technology, visibility, and timing. Observing a fast-moving object like 3I/Atlas is a race against geometry. As it entered the inner solar system, solar elongation dropped below 25 degrees, bathing it in glare. Even an 8-meter telescope struggles to isolate faint features under such conditions. Yet Chinese facilities, including Xinglong 2.16 m, Lijiang 2.4 m, and Ali 1.8 m, continued imaging successfully. Their edge was not mirror size, but flexibility. Automated mounts could reorient within 5 minutes of alerts. By contrast, Western observatories faced months-long scheduling, priority reviews, and safety protocols. Elongation drops triggered instrument safe modes, while maintenance, calibrations, and planetary targets consumed observing time. Even Gemini's twin 8-meter mirrors couldn't pivot instantly. Flexibility, not raw power, proved decisive. Chinese teams, with wide-field high-resolution CCDs exceeding 10,000 times 10,000 pixels, captured evolving tail morphology when others could not. AI-assisted pipelines process frames in under 2 hours, allowing same-night releases. In the era of transient astronomy, speed is everything. While Western observatories coordinated meetings, Chinese networks tracked outgassing patterns and micron-scale dust movement. For the first time, a major cosmic discoveries narrative was shaped outside NASA, ESA, or ESO, driven from Beijing, Yunnan, and Tibet. It was logistics, visibility, and readiness, not suppression or sabotage. In space science, readiness means legacy, and that shift rippled beyond astronomy into geopolitics and prestige. For over 50 years, global astronomical infrastructure centered on Western leadership, from Hubble's 1990 launch to JWST's 2021 deployment. Control of space observation was American and European. 3. Atlas signaled a potential eastward shift. As NASA went silent and Chinese observatories filled the vacuum, the story expanded beyond a comet. Power, access, and reputation were at stake. Each Chinese image was both contribution and statement, asserting that cutting-edge astronomy no longer resided solely in one hemisphere. For the global community, it was a wake-up call. Knowledge had decentralized. Control of critical sky data governs discovery narratives, publication priority, and historical record. A single time-stamped image can alter credit for a finding. Western institutions assumed open data ensured open leadership. China demonstrated that transparency itself could be strategic. The comet's journey mirrored a subtler terrestrial shift, a rebalance of scientific storytelling. It was not hostile competition, but evolution. The cosmos rewards preparedness, not monopoly. Beneath politics lay a practical question. How can the world ensure data from one telescope is trusted and shared globally? More telescopes observing highlighted infrastructure fragility. Only a handful of facilities could track a fast-moving interstellar object across changing light. Downtime in any nation crippled coverage. ESO and NAOC proposed an emergency distributed observation framework, where telescopes across continents automatically share transient targets within 30 minutes, standardizing calibration, exposure, and release. 3. Atlas made that urgent. The comet, indifferent to politics, raced outward, data decaying with distance, meaning trapped in partial archives. Astronomers felt the ticking clock. Every comet is a chemical laboratory. For 3I/Atlas, stakes are magnified. It hails from beyond our solar system. Chinese frames captured its green coma, expanding to 600,000 kilometers, deepening as sunlight broke molecules apart. Gemini South spectroscopy from August 2nd to 5th, 2025 confirmed the CO2/H2O ratio at 7.6 to 1. Alignment of these datasets provides humanity with a verified map of extraterrestrial chemistry. Divergence risks losing calibration against alien material. Chinese astronomers noted subtle morphology changes, a faint anti-tail, and a dust plume detaching, missed by Western observatories due to glare. A comet fragmenting at 60 kilometers per second evolves every 90 minutes, faster than any current telescope coordination allows. Collaboration, not competition, is required. Interstellar objects follow one-way paths. Their physical truths vanish once gone. Observation windows last weeks. If half the world's instruments are silent, discoveries evaporate. ESO calculated a 30-hour gap observing Borisov cost 15% precision in outgassing curves. Multiply for 3I/Atlas and losses compound. Lessons are clear. Global protocols must ensure shared visibility and rapid data publication. A planetary network or astronomical emergency system could function like seismographs for the sky. Automatic triggers, cloud-based pipelines, mandatory transparency. China's efficiency proved agility works. Openness must meet it halfway. Otherwise, 3I/Atlas risks becoming a monument to failed coordination. By September 2025, 3I/Atlas receded into the inner heliosphere, apparent brightness from Earth dropping below magnitude 13.5, lost in solar glare. Only Mars Express, Trace Gas Orbiter, and MAVEN instruments could still collect meaningful data. From Earth it was gone. The universe moved on, Humanity debated what was lost, data or unity. Its hyperbolic excess velocity, 26 km/s, ensures it will never return. Every image, every spectral line is now a fossil. The sky delivered a message while humanity argued. Scientists call it the tyranny of elongation, geometry hiding truth just as it becomes most interesting. Our institutions mirrored this, bending away from transparency when discovery demanded it. Chinese observatories continued posting delayed releases into September, showing a shrinking coma, green fading to pale blue. Analysts compared these to JWST August spectra, attempting cross-calibration, yet gaps persisted. Even 0.2-second timing offsets misaligned frames, misrepresenting dust jets or tail density. These are coordination errors, not physics. Still, 3I/Atlas has taught more than we realize. Celestial events ignore politics. The cosmos does not censor, it moves. What remains are echoes, lessons in readiness, humility, and that discovery belongs to those alert when others blink. The story of 3I/Atlas extends beyond astronomy. It exposes cracks in infrastructure, delayed releases, uneven access, fragile collaboration. Yet it also reveals potential. In 2025, distributed observatories across continents collectively captured an interstellar object at high resolution, from ultraviolet Hubble spectra to 900 nanometers optical images from Legion. Humanity solved half the challenge. Geopolitically, China's rapid response shows what national investment in flexible science achieves. Funding numerous smaller, autonomous, rapidly scheduled facilities built an agile network. Western agencies face a choice: adapt. Redundant, globally connected telescopes, perhaps under the UN Office for Outer Space Affairs, could safeguard astronomy from downtime or politics. 3I/Atlas is a case study in cosmic